Okay, let's keep trucking on with this concept of numerical representation in science. A really important reason why we care and we have a whole system on how to represent numbers in chemistry and science in general is because we want to convey precision and accuracy of our values. There's a lot of nuanced meaning behind how we represent our data, just like in art, right? There's a lot of nuanced meanings behind music, harmonies, melodies, okay, artistic color palettes, and so forth. So a really important thing is that when you are writing values, it's really important that we have to consider error or lack of precision and accuracy, sources of that. So quick note on types of errors that can exist in experimentation. The first is systematic error. Okay, systematic error is like consistent error throughout an experiment. So like, let's say you always have the temperature 1 degree too high, but it was consistent throughout the entire lab. Or you always calculated a value, a mathematical expression with an additional division by a factor, but you were consistent throughout your entire calculations. That would be systematic error. It really affects mainly accuracy, but it doesn't affect your precision too much because you're consistent. Okay, so the main issue is error is affected. Okay, or error, sorry, accuracy is affected. I think it's the A affected. I'm not an English teacher. So next thing is random error. That's like you drop something on the scale once for one trial and it kind of threw off your findings, or you have what we call outliers, right? It usually is an kind of instantaneous, instant/temporary error that usually connects with outliers, all right, in data. This type of error affects both your precision and accuracy, right? So this affects both precision and accuracy. All right. We really do not like random errors, but unfortunately, that is the type of error that you will most likely encounter in our labs because you're trying to figure out how to do lab, right? How to work equipment. One thing that we say in a number is that we always say the last value in a given measured or calculated number is what we call the uncertain digit. The indigit, so like let's say for 8.073, we would say that the uncertain digit is this last digit. This is where we often get error margins of 0.001, where you could say, well, at that digit holder, at that placement, there's a high probability that that number's off by a little bit. All right. Error margins are, and if you looked at Grab's very much research, you will find that error margins are actually calculated through a little bit more of a mathematically complex way, but the concept is that it's trying to show you the range at which your equipment, your math could have been unprecise. Okay. A common final step in values that you obtain during lab is to calculate the percent error. We're going to talk more about this later when we talk about chemical reactions, stoichiometry, and so forth. But I do want to put out there, just because we're talking about uncertainty, that percent error for a given lab where you know that you should get a certain value, percent error is calculated through saying the experimental value minus the actual value, what you should have gotten, all over the actual value times 100, okay? That's how we kind of calculate how off, whether it be under or over, our experimental data is compared to a set accepted value, all right? This, by the way, this formula can be written in many ways if you Googled it. I just like the term experimental and actual because we're talking about experimentation. So there you go. You're welcome to work on the practice problem below. I don't feel like this is a crazy concept, so I'm going to go ahead and let you do that, and I'll download the answers in the filled in PDF. Let's move on now to the big topic, which is Sig Figs. How do we represent precision in just the way that we write our numbers? All right, so Sig Figs is basically, now by definition, I mean, how would I describe it? Sig Figs is basically a method of representing precision in your measured / calculated values. And it goes by a set rules. These rules you're just going to have to work with to understand. Sig Figs is one of those kind of technical skills that you just kind of have to beat over and over and over through practice. And there's not much huge concept behind it, okay? So the first rule is that all non-zeros, so numbers that do not equal 0, all right, are significant. We say that any value calculated or measured that comes out to be not a 0 is a significant digit. It holds certainty. It holds, I can't use significance, but basically that. Zeros before a non-zero are not significant. We call those, what do we call those? 1 second, let me think to myself. Okay, I figured it out. We call those leading zeros, okay? We say those are leading zeros. So an example would be a value of 0.000063. We would say that these zeros right here are leading zeros and they don't hold that much value. And but I'm not saying they aren't necessary, okay? What I am saying is that they're not significant when we talk about what this, as a scientist, what I'm reading to look at those numbers, but they're definitely necessary to keep the overall magnitude of the value being represented. So do not mistake Sig Figs as changing the actual true magnitude. It's more of a you know what? I should probably just stop talking now and just kind of keep going through the rules. So the third rule is zeros between non-zero numbers are significant. Okay, we call those, well, I don't know actually if there's a technical term for it, but I like to call them the sandwich zeros because they're sandwiched in between, all right, to significant digits, which makes them significant, all right. The fourth rule, zeros following a decimal only after a non-zero are significant. So an example of that would be, all right, 6.007. Okay, this kind of serves as a double whammy example because it also shows a sandwich zero as well as the idea that after a decimal, those zeros count. Okay, so that's kind of an example to go with rule 3 and 4. Finally, zeros following a non-zero with no decimal are not significant. We call those trailing zeros. They trail behind, trailing. Right, an example would be 6000000, no decimal. Notice something. One of the crucial aspects of these rules is it's all about decimals, with the decimal placement I should put. So let me just abbreviate that even more. It's all about decimal placement. Where your 0 and your values fall in relocation to the decimal is all like the determining factor, basically, decimal point location. So let's look at some examples. If I have a value of 6.7300, what are my significant figures? How many of those digits are actually significant to me as a scientist? So I would look at this and say, well, first of all non-zeros are significant. So automatically, according to rule 1, these 3 count. Right there, I have 3 Sig Figs, okay, at least. But what about these other 2 zeros? Well, let's look at rule 2. Zeros before non-zero, we don't have any of those, so skip over that. How about zeros between non-zero numbers? We don't have any of that. How about zeros following a decimal after are significant? That's us. So we would count those 2 zeros, and now we have a total of 1, 2, 3, 4, 5 significant figures represented in this value. Let's try another value. Let's do another example, and I'll switch to black. How about 6.073? Let's look at how many Sig Figs that would have. All right. So again, all non-zeros, significant. Bam, automatically 3. Zeros before non-zero, still not applying to us. How about zeros between non-zeros? Here we go. That would make this 0 significant. So I have 4 Sig Figs. The more Sig Figs, it means the more precise and certain you are. So it's kind of a backwards sidetrack to standard precision, but it's the most important nuanced way that scientists convey their data, convey their values. So this here, I would say, is far more important than understanding basic precision. This right here is the ticket for scientists in representing their precision to the scientific community, okay? Let's look at one more example. Let's say we have 60000. Okay, how many sig figs is this? Well, one non-digit, bam, one sig fig. I have 4 zeros afterwards. And if there was a decimal before it, they would be significant. But notice, I did not put a decimal at the end. Okay, therefore, I'm showing a lack of precision and certainty in those digit places. So in fact, my precision is only in this value, 1 sig fig. Very low precision, very low significance being held by this value, all right? So it's a little bit of a new way of thinking, but you guys will get a hold of it later. Quick rules, how do you do sig figs when doing math? So let's say, because very rarely do we just work with a value by itself. We often combine it in some mathematical expression, plug it in, so forth, right? When we multiply or divide, so let's say I have 7 point, oh man, I'm gonna make this easy on myself so I can do mental math. Hold on. Let's say I want to do 6.4 divided by 2. All right. And I'd get a value of 3.2. Well, when I look at my sig figs, my only sig figs here is I have a sig fig of 1 for this value, 1 SF, and a sig fig of 2 for this number. According to my sig fig rules with math, you can only count sig figs for the least sig fig value. So what I mean by that is that the least sig fig value determines your final sig fig value. So because I have a value in my math, right, that is only 1, oh, that was a terrible color. That is only 1 sig fig. Okay, I'll just highlight it like this. This sig fig determines the sig fig count of my final answer. So in fact, my final answer can only go to the first sig fig. Therefore, my final answer would have to be 3 according to my 1 sig fig rule. Okay. When you're adding or subtracting, it's a little bit different. It's a little bit more similar to our basic understanding of precision, which is when adding or subtracting, we go off of the least precise, okay, variable. So let's look at an example. Let's say I have 6.4 plus 2.73. Instead of necessarily counting sig figs in the beginning, I can just kind of look at my least precise value and say, well, it is to that digit holder, okay, which gives me a 2 sig fig. Often you'll find that these rules kind of cross over, but there are examples where they slightly differentiate. You'll just have to figure that out as you go. But this would mean that my value was originally, okay, oh boy, math, 9.13. Good Lord, I hope I have that right. And in order to obey the sig fig rule when doing adding or subtracting, my final answer can only be to 2 sig figs and specifically to the 10th decimal place. So it would be 9.1. Quick note, conversion factors have no effect on sig fig. So if you're using an equivalent of like 4 quarters to $1 or 2.54 centimeters is an inch, the sig figs in these conversion factors do not impact your final answer. Why? Because they are math tools. And math tools are considered exact numbers. We call them exact numbers, all right? It's like saying they're a constant. That's another way of putting it. They act like a constant. So there you go. That's all I have for Sig Figs. Best of luck. Go ahead and go to your workbook and try out some of the example problems.